Okay, welcome everybody. So this is, I think, our fourth class, maybe. And let's see, are there any questions before we start?
Professor, I have some question.
Okay.
So regarding to our homework,
Yes.
okay, like the first set of homework, 4 ways to represent a function, part 2, question 13.
Okay, one second. Let me go to it.
Yes.
Okay. Four ways, part 2.
Yes, and question number 13.
30, okay. 13 or question number 13?
13, sorry.
13, okay. Okay. Yeah, so it says find a formula for the described function, right?
Yes.
It says an open rectangular box
Yes.
with volume, and then it has some number meter cubed, has a square base, right?
Yes.
Okay, so it's a rectangular box with a square base. And express the surface area,
Yes.
A, of the box as a function of the length of a side of the base X.
Yes.
Okay, so so the volume, they tell us the volume, right?
Yes.
So from that, you can determine the, I guess what we call the height of the box, right?
Yes.
So then you know the height and the base length side, right?
Yes.
So from that, we know that a rectangle has 6 sides, right?
Yes.
So you can calculate um, the you can
Surface
calculate,
area.
yeah, you can calculate the surface area, right?
Yes, but like here, this rectangular box, I think that it has a square space that make it has like 2 square base, right?
Yeah.
So it's the one like it should be like. I think the answer is wrong. Can you check it?
Well, the problem is that everybody's going to have a different answer because the number that when they say at the beginning, an open rectangular box with volume, then they tell you the volume, right?
Yeah.
What does your volume say?
My volume is like 4.
Yeah, that's the thing. It's different for each person. So we have to do it together.
Yes, can we do it together?
Okay, I think so. Let me get my thing here. And let's see, I need the pen. Okay. And let me just take a screenshot of this problem. So I have to go to here. Go back to there and get the, so go to edit. You on here? Okay, so 13 is here. Here. Copy that. Then I have to go to here. And I have to go to here. And then go to Yes. Okay. Okay. Okay, let me share my screen. Okay, so there's the problem, right?
Yes.
Okay, so it says that okay. Well, let's see. It says that this time it says the volume
7.
is 7, like that, right?
Yes.
And we have a box, I guess. It's a square here.
Yes.
This is X, and then this is the, I call it the height,
Right. Yes.
and the volume is X squared H equals the volume,
Yes.
and um, so that's equal to 7. So we can say that X squared, I'm sorry, we can say that H equals 7 over X squared, right?
Yes.
So now what? Oh, the surface area, right?
Yes.
So we need, let's see, we have 2x squared because we have this surface area and the one on the other
And
side.
you right.
And then plus, we have, this is x by h, right? And it's 4 times x times 7 over x squared, right?
Yes.
So we get 2x squared plus 28 over x, right?
Yes. But I believe that the answer is only like the answer is said that the surface area is x squared plus 28 over x. There's no 2x squared.
Oh,
That's my answers. I don't know why.
mm,
It's supposed to have like two square base. So that's make it like 2x squared plus something behind. But the answer show out that it's only like x squared plus blah blah blah.
x squared plus
Yes,
8
like
over.
it's missing one square base. You can try to type down in the web assign page and see the answer for yourself.
Right, but do you agree with this though?
Yes, that is my answers.
Uh, okay, let's
Professor,
talk about it. Maybe after class we can talk about it.
Yes.
Professor, can I interrupt?
Yes,
The
please.
question say it's an open rectangular box, so it's only 5 sides instead of 6.
Ah,
Oh,
Yeah, thank you.
ah. Okay, he's right. Thank you for that.
thank you.
Thank you so much. Okay, any other questions? Okay, so uh, let's go to here. No, go to here. Okay, and let's go to, okay. So let's go to here. Okay, I will share my screen. Okay, can everyone see my screen?
Yes.
Okay, so we'll have a little some group group discussions after this, and then a little group quiz and and then a single individual quiz as well. Okay, so after this video. Okay, let's discuss another topic. Oh my God, how did that happen? That's ridiculous. Let me try that again. That is not supposed to happen on YouTube. Why did it do that? Let me see if I can fix that. Ugh. Let's see. Edit. Okay, let's see. Edit, end screen, more options. Let's see if I fixed that now. Try it again. Okay. Okay. Oh, why is that? What a disaster. Hmm. Okay, hang on 1 second. I don't know why this is happening, but let's see. Figure this out. Audience. Hmm. Hmm. Why is that? Hmm. I can't understand it. No, I have no idea why this is. Title, functions, playlists, end screen, cards, audience, thumbnail. Not age restriction. Oh. Hmm. Ah, no. Okay, I'll try it one more time. If it doesn't work, I'll give up. Okay, maybe it's working now. Okay, let me try that again. So let me share my screen again. Here. Okay. Okay. All right. Let's discuss another topic in regarding functions. and this is called piecewise defined functions. So here we have a so-called piecewise defined function. Can everybody hear this?
Yes, Professor.
Yes.
Yeah.
I can.
What? You can hear it. Okay. So what does it say? It says this is what f of x is. So what is f of x? We use these big brackets. And what we do is we say, okay, whenever x is less, you mention a range here. So anyway, whenever x is less than 1, use this formula to find out what the height is. Whenever x is greater than or equal to 1, use this formula to find out what the height is. So what does that mean? So whenever x is less than 1, so let's put 1 here. Here's 1. Okay, so whenever x is less than 1, so everything from here on over, use this formula. So we know what this graph of this formula looks like. So we know it looks something like this. It's a parabola. And I use the dotted line here to indicate that we're not using that when x is greater than 1. We're not using this formula. So I don't want to have the line there. But here, this is just a parabola. So if I want to know, for example, when I put in -2, for example, like that, then of course I know that the height, because I'm using this formula, that I know that the height when I put in -2 should be 4. So in other words, it's -2, 4 is the coordinates of this point. All right. Well, let me undo that. You know that it continues. Can't draw it very well, but continues. So -2, 4. And so when x is -2, it's 4. That is, we're using this formula. However, we don't use that formula over here. For example, when x is 2, we don't use that formula because this is only use this formula when x is less than 1. So what do we use over here when x is equal to 2? We don't use this because it's not less than 1. So this one applies in that case. So when x is greater than or equal to 1, use this formula. So if I put, so I'm supposed to use this. So if I put in 2 into this, what do I get? I get 4. So where's 4? I already put 4 up here, so I guess this is 4. So I'm talking about like something up here. Now it looks like it's right on that parabola. In fact, it is. But that was just a coincidence that I chose 2. Let's put in 3. So what would I get for 3? So here I would get, I'm using this formula because x is 3, which is greater than 1, so use this formula. So I get 5. So where's 5? I don't know where 5 is, but maybe it's here. Something like that. Okay. So yeah. So actually, if I wanted to graph this, this is actually y equals x plus 2, and we know how to graph that. So if this is 4, this was about 2. So this is the line y equals x plus 2, looks something like that. But I don't want to use, I'm only using it to the right of 1. So all of this to the left should be a dashed line. So let me try and do that. So it might look something like that. That's not a very good picture, but you get the idea that this formula here only applies to the right of 2, or to the right of 1, or actually right at 1, because this is greater than or equal to 1. So this one starts at 1, and this one goes up to 1. So actually the way we would do this is we put a solid circle there, and we put an open circle there. And that would be to indicate that this one has, this formula here has the greater than or equal to sign, and this formula here has only the less than sign, not less than or equal to. So we put a circle here, and it would look like that. So all of this is called a piecewise defined function. So actually we're not limited to just having 2 pieces. We could have as many pieces as we want. Like here we have 3 pieces. So this says when x is less than 1, do one thing, use one formula. When x is between -1 and 2, do something else, use this formula. When x is greater than 2, do something else, do this formula. Of course, we could change it. We could have as many pieces as we want, and that would give you some kind of graph where when I'm not going to try and draw this properly, but when x is less than -1, use some formula. So 2x plus 1 looks like 2x, so here's 1, slope of 2, so it's probably like here, maybe, I don't know what it looks like really, but let's say it looks like that, and then, you know, it would be like dots up here, we wouldn't use that part, and then when x is between -1 and 2, so up to 2, maybe 2 is over here, use a parabola formula, so whatever that looks like, -1 I guess would be 1, and this would go like that, and go up to like there, something like this. And then, and these would, by the way, since these are less than or equal to, these would be filled in like that, and this would be filled in like that, and this would be open like that. And I don't know if I drew this correctly or not, but I'm just, and then when x is greater than 2, use x plus 5, so I don't know what that looks like, but maybe this was 4, so this is x plus 2, 7, so it might be like this, something like that. So this would be the picture now. So this would be a piecewise defined function with 3 pieces, and you could have as many pieces as you want or as you need. Okay, so now let's go to the tests on Manaba. So please go to the Advanced Math Test section, and I will give you a question to do with a group. So I'll put you in groups right now. And then check on Manaba and I'll give you a test. Uh-oh. Oh no. Okay, there was a problem, and that is the test didn't show the image, or didn't show the function. So I don't know if that's true of all of these, but I prepared all these little short tests for you, but seems like they don't, I'm not sure if they have the images or not. So you can't do them without the image. Let me just check another one, see if it's got it. No. Okay, so these are missing. Okay, so we can't do that today. Okay, let's continue without that. What should we do today? Let's see. Okay, I'm going to start on something else then today because I didn't prepare for this today, but I'm going to start on something else today, and we're going to come back to this next time. Okay, so let's take a look at an introduction to limits today. Okay, so. Okay, can everybody hear me okay?
Yes, Professor.
Yes, Professor.
Yes, Professor. Yes.
Yes.
Yes, Professor.
Let's see. Okay, so let's take a look at this, and I'll use my pen if I can figure out how to do this. Okay. So last time we talked about this issue of the, well, we talked about a circle, and then we talked about, we're all familiar with the concept of a tangent line to the circle. So that's what this picture is. Okay. And then we said, well, we can sort of easily imagine what we mean by the tangent line to a curve. So if you have a curve like this, and the tangent line is there. And we also talked about why we might like to be able to find that. And we mentioned one example, and that was when we have a, what was it, time and distance. So that is, if we have distance, which is a function of time, and we have some curve in that plane, so then it turns out that the tangent line has some particular meaning. The slope of the tangent line has some meaning. Can anybody remember what that was? Pardon me. Has some meaning. Do you remember? No? Okay, it gave us the speed. So anyway, that's why, that's some reason why we might like to solve this problem. But let's just talk about how to solve it. So here's a question, example 1. So it says, find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. So here, this is the y equals x squared parabola, and here it is. And one of the points on there is when x equals 1, when we take f of x equals x squared, then f of 1 is 1. So we know that one of the points is 1, 1 right here. So what we want to do is find the equation of this, I think it's the red line there. Okay, we want to find the equation of the red line. Okay, is this clear?
Yes.
Yes, Professor.
Okay. So they say we will be able to find the equation of the tangent line, I guess they're calling the tangent line T, as soon as we know its slope M, right? We need to know the slope. So that's what we're aiming at right now. We want to know the slope of this red line. The difficulty is that we know only one point P on this line. So normally if I gave you a problem, like I said, find the equation or find the slope of the line that goes through the point 2, 3. I said, find the equation of the line that goes through this point. What are you going to say to me? So I'll say it again. Find the equation of the point, find the equation of the line through this point. What are you going to say to me?
Possible.
It's not possible. Why?
There's only one point.
There's only one point. So in other words, there's infinitely many lines, right? So there's not one line, so you can't find the slope, right? There's no one slope, right? Okay, so they say the difficulty is that only one point P, that is that we know only one point P on this line, whereas we need 2 points to compute the slope, right? Everybody knows that, right? When you have 2 points, then you can calculate the slope of the line, right? But observe that we can compute an approximation to the slope by choosing a point, a nearby point, q x comma x squared. Okay, so give me suppose I have a point here. If this is x, what are the coordinates of this point? I have to give you the name of the, oh, sorry. What are the coordinates of that point?
X comma x squared.
Yeah, x, because the x coordinate is x. And then we know since it's on the parabola, its y coordinate has to be what? X squared. So every point on this parabola, we can express it as having coordinates x comma x squared, and then it just depends on the particular x that you're talking about. So that's what they've done here. Some arbitrary point q will have coordinates x comma x squared on the parabola. And computing, so what we can do is we can compute this. Why can we compute this, but not the slope at P? Why we can't compute the slope at P, but why can we compute this?
Because we have 2 points.
Yeah, because they said we have these 2 points. So one is this point, P, and then here's another point up here, Q. So if we have 2 points, we can compute the slope of the line that joins them, right? But is that the slope that we actually want in the long run?
No.
No. Why? What do we want in the long run? Maybe I need to make colors here. So we can compute, I cannot draw here. That's supposed to be a line. We can compute the slope of that line, but we cannot compute the slope of what? Of this green line. That's what we really want. We want the slope of the green line, but we can't do that because we only have 1 point for that. Did everyone get the problem? Does everyone get the problem?
Yes.
Yes.
Okay. So, so what this is though, what we can compute, because this is from P to Q. So how do we get that? Well, the coordinates of P are 1, 1, and the coordinates of Q are x squared. So we take the y coordinate of Q, which is here, x squared, minus the y coordinate of P, which is 1. And then we take the x coordinate of Q, which is x, and the x coordinate of P, which is 1. So we get this. So we get x squared minus 1, x minus 1. Okay? So they say, for example, for this particular Q, we can fill that in. And when we fill it in, we fill in the Q, we square it, or whatever. We fill this in, and we end up with this. So we did get the slope of the orange line. We did just calculate the slope of the orange line. But that is not the slope of the green line. However, the idea of calculus is that we draw this point here, Q, closer to P, and then closer still, and then closer still, each time we compute the slope of the orange line that we get when we connect the points. So they say here that if we use x equals 2 as our first one, so up here, then we get a slope of 3 when we do this formula. Then when we use x equals 1.5, so like here, and we put that into the formula, then we get this number, 2.5. Then we get a little bit closer to P, and they say use 1.1. So that's here, 1.1, and we put that into here, and we get this number. And then we get even closer to P, and we get this number. And then we get even closer to P, very close to P, and we get this number. Does everyone follow what we're doing here?
Yes.
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 Okay, so
Yes,
look at this.
Professor.
So look at this sequence of numbers. We got 3, then we got 2.5, then we got 2.1, then we got 2.01, then we got 2.001. So we can kind of guess what it's getting closer and closer to. We might not be right, we could be wrong, but we could make a guess anyway. What is it getting closer and closer to?
2.
Certainly seems like it's getting closer to 2. Now, it might not be. It might be getting closer to 2.0000001, and that's never gets closer. That's what it's getting closer and closer to. But it looks like, anyway, that it's getting closer and closer to 2. So what are we doing again? We're taking Q and moving it closer and closer. So we can write that like this. Q is getting closer to P. Okay, that's how we write that. Q is getting closer to P. Okay, maybe you don't like that notation, or maybe you do like it. It doesn't matter. That's the way other people will write it. They're going to say Q is getting closer to P. And each time when we do that, what are we calculating? We're calculating this, right? For each Q. Does everyone understand that?
Yes.
So we can write MPQ. That's what we called this, MPQ. So we're looking at MPQ and doing it, checking Q, getting fairly close to P, then closer to P, then closer to P, then closer to P. And we saw it looks like this. Well, I said it looks like that. Okay? So what we think is that this is 2. And we might be wrong, but what we think is that this is 2. Or we can rewrite this using the formula, which is here. And so we can say what we think, one more thing. Q getting close to P, let me draw it again. So we have the curve, and here's P, and here's Q. And the coordinates of P are what? What are the coordinates of P?
1.
1, 1.
1, 1. So the x coordinate is 1, right? The x coordinate is 1, and Q has some other x coordinate. Now as Q gets closer to P, moving along here, x is getting closer to what?
1.
1. So instead of saying here, we said Q gets close to P, we can also just say x gets close to 1. So that's what they did. They said x gets close to 1. So we said this is maybe equal to 2, and we can rewrite this. Instead of Q gets close to P, we can say x gets close to 1. And instead of saying this thing here, we can say what it's equal to, which is here. So that's what they did here. So we're thinking that it might be 2. Is this clear?
Yes.
Now, if it was 2, if that's correct, the original question was not just to find the slope, but the original question was find the equation of the tangent line, not just its slope. That's a little bit more work, but not much. We just want, once we know the slope, we can probably find the equation. Why do I say that? Because, let me draw it here again, because, now that's really a bad example. I can't even use that. That's too bad. Let me draw it up here. So let's try this. That's really bad. And then, well, let's try this. And then here we have the, there it is. Here's P. And what are the coordinates of P again? 1, 1. Now, if we find out that the slope is equal to 2, then we have a point on the line. And the slope, yeah, we can definitely find the equation, right? What is the equation? It's y minus 1 equals 2 times x minus 1. So that's pretty easy to do. And then we just write it as y equals 2x. This is minus 2 plus 1 is minus 1. Is that right? I think that's right. So what did they say? Let's see if I got it right. Yeah, there. Okay, so we could find the equation. Okay, but it was all kind of a guess. It was just a guess. Why do I say it was a guess? Why do I say it was just a guess?
Because it can have like multiple decimals after.
Yeah, because we only guessed that this was equal to 2, right? We might have been wrong. Who knows if it's really 2? We don't know that, right? It looks like it's 2, but just because it looks like it's 2 doesn't mean it's 2. Right? Does everyone agree?
Yes.
Yes.
Okay. Now, actually, they did it. Not only did they do it starting at 3, let me go back here again. Let's go to here. Not only did they do it, where was it? Here was it. Here's 1. And they started at, I think they started at 3. They up here. Q was originally here, and P was here. Not only did they start at 3 and then come to whatever it was, 2.5, and then 2.1. What was it? Wait, sorry. Not only did they start at 2, 1.5, 1. Okay, so sorry, that was wrong. So not only did they start at 2 and then do 1.5 here and then 1.1, but they also checked it over on this side. So they start over here. Where did they start? I didn't notice that, but they also started at 0. So they started here and calculated the slope of this line. Okay, now this is going to be very bad there. Of that line, and then that was at 0. Then they probably brought it into closer to like 0.5, and then maybe 0.9. So they kept they checked the lines like this. And the results there, I didn't notice it, but the results there, they start at 0, they got 1, then they got 1.5, then they got 1.9, 1.99, 1. So it definitely looks like it's going to 2, right? This side looks like 2, and this side also looks like 2. But just because it looks like 2 doesn't mean it is 2. Okay, but anyway, that's why I said this is all just a guess. So this is really just a guess. Okay, so everyone get this idea? Okay. All right, now let's keep going. So you can see the picture. Oh, they had all these nice pictures I didn't know. Okay, here's Q, then here's Q, then here's Q, then here was Q, then here was Q, then here was Q. So you can see they keep moving Q closer to P. And each time they calculate the slope, and we saw the basic results. So it looks like 2. Any questions about this? Okay, here's the velocity problem that I mentioned earlier. So I'm not going to go through it again, but here we have, I think last time I told you that usually people use S for distance, but I use D. So I had D as a function of T, but they're saying S is a function of T. And they're using, for their example, this function, 4.9 T squared. Okay, and if I graph that function, that looks like a parabola. Like that. And then as I argued last week and I reminded you of this week, in that case, this slope tells us the speed. So that's why we would want to do this. So anyway, you can go through some kind of argument like this to make an estimate of what the speed would be at 5 seconds, okay, after 5 seconds. So the same kind of argument, this would be 5. So at 5 seconds, what's the speed? You could go through the same kind of argument. It looks like the speed turns out to be this, for this object. Okay. Any questions about that? Okay. So now we come to this discussion, the limit of a function. And we just saw this thing like this, LIM. Okay, can anybody remind me what I should put in the rest of here?
X approaching something.
Yeah, okay. What was it in that discussion?
1.
Good. And then what else do I have to fill in here?
Function.
Yeah, right. And what function was that?
X squared minus 1.
Okay, okay, good. So, okay. x squared minus 1
Divided by x minus 1.
Right, so we just looked at this. This is what we just spent the last 15 minutes looking at, right? Does everyone agree?
Yes.
Yes.
And we made a guess. We made a guess that this is equal to 2, but it was a guess, right?
Yes.
Okay. So now we want to understand this kind of problem. So maybe we won't have to guess anymore once we study this carefully. Okay? So before we say we want to study this, what are the different pieces in here in this kind of question? So what we're going to have, we're always going to have this word LIM. That means we read that as the limit. We're always going to have that. We're always going to have an arrow there down in the bottom there. And we're always going to have some function in here. This is a function. Does everyone agree this is a function?
Yes.
Yes.
Okay, so this is a function. So, but in general, we're not going to be always stuck with this function. We just want to we want to be able to deal with this in general. So we're going to say we're going to have some function there. It could be this function, but it could be some other function. It could be x cubed, just x cubed, or it might be 100x cubed, or whatever. Any kind of function, but it's going to go in here. All right? And then we have to have some piece here and some piece here. So what kind of piece goes here and what kind of piece goes here? If we're going to follow what we did before, what do you think goes there and there?
X and 1.
Well, x and 1 went there before, but what do you think in general goes here?
X.
Yeah, a variable goes here. And what goes here usually?
Number.
Where it
Some number,
pushes.
right? Yeah, some number, or maybe some constant. Whatever, a number, a constant, whatever you want to call it. Okay? So we're gonna, I could put a 5 there or whatever, but I'm just putting this to indicate that it's some number. Okay, so we're gonna have a variable here and some number here. What goes here again? Some function. And then the answer is generally gonna be what? Is it gonna be an arrow? No. Is it gonna be a face? No.
Number.
It's going to be probably a number. Now, not always, but it's probably going to be a number. So let's call it K1. This is K and K1. Okay? So this is the form that we're going to study. All right? So let's just make up something. For example, we might end up studying something like this. The limit as x cubed of x cubed as x goes to just any number I want to put here, 10, and then I get some number out here. I don't know, maybe it's 3,000. I don't know. I have no idea what it is, but that doesn't matter. I just want to explain the form. So here is going to have a function. Here we're going to have an arrow. So what does this mean down here, by the way? This is the kind of unusual part of this. What does this mean?
Assume that x goes close to
Yeah.
10.
It means that, remember, it meant what? It meant that let's say this one, here was 1, for example, and this was x. The coordinates of this point, the x coordinate of that point, that was x. So it's as this thing gets closer to some number. So we're going to be moving this closer and looking at something. Now, we're not necessarily going to be looking at this. We're just going to, I said, we're talking about this as x maybe goes to 1. What goes in here is just a function. It doesn't have to be that function that we saw before. It doesn't have to be x squared minus 1 over x minus 1. That was just one, that just happened. But we want to study this in general, so we don't want to limit ourselves to this, just some function. As x moves closer to some number, and then we're asking what happens to this function, or what happens to this function as x gets closer to 1. All right, so let's go back and look at that. Okay, so here's an example. So let's just identify the pieces. Just identify the pieces. So I said there should be a function. So what is the function here? Let's start even here. There has to be an equal sign. So where's the equal sign? Obviously the equal sign is here. Okay, so where's the K1?
4.
4. So the number that it's getting closer to is 4. That's the K1. Okay, so where's this function?
X squared.
6
X squared minus x plus 2.
Yeah, the function has to go after the limit word. The function has to go after the limit word. So has to come between the limit word and the number. So it has to come in here. So where is it here? It's right here. So what is this function that we're examining? It's f of x equals x squared minus x plus 2. All right, now what is this thing? How do I graph this? What does that look like? Well, fortunately, we don't have to think about it because it's right here. Okay, so it looks like that. Okay, so it's a parabola, right? This is a parabola. And it's a parabola that is upward facing, not downward facing, right? It's upward facing. Okay, so this is the graph of this looks like this. All right? So what are we asking here when we write this part here? In the purple, what are we asking? What's the function?
Square minus x plus 2.
Right, so that's this graph over here. Okay, so we're asking something about this graph, some question about this graph. Now, what question are we asking? We're not asking anything about slope. That just was before. That was before. Now we've divorced ourselves from the question of slope. We're just saying that before we had this, which was the slope of something, but now we're not saying it has to be the slope of anything or anything like that. It's just a function. So we're not asking anything about slopes now. So what are we asking about right now? Here's this function, or here's the graph of this function. And we're talking about when x gets close to 2. So here's x equals 2. And what we're asking is, what happens to this function as x gets close to 2? So that seems like an incredibly simple question to answer. It's not complicated. It's just simple. Or if you want to make it even easier, maybe this function is a little complicated for us. Let's just make a really simple question. Let's say, instead of that function, let's just say the function y equals x squared. Why make it hard? We can make it easy. Okay, so here's y equals x squared. And here's, we'll use the same number 2. And then the question would be not what happens to this yellow function, but what happens to just x squared as x gets close to 2. Now that's a simple question. There's no mystery there. It's obvious. What is the height when x equals 2?
4.
4.
4. So all this is saying is, as you get close to 2, what happens to the function? Now, when we use the word, what happens to the function, when you're thinking about it graphically, the function means the height of the graph. So that's what the function means when you're thinking about it graphically. So if I ask you what's happening to the height as x gets close to 2, it's obvious. What's the answer?
It approaches 4.
Yeah, it's getting close to 4. It's obvious. I mean, there's no other answer, right? As x gets close to 2, the height, in other words, if x is equal to 3, what do you get for the height? You get 3 squared, which is 9. And if x is 2.5, what do you get? Well, you get something between 9 and 4. It's here. And if it gets closer, it's getting closer here, here, here. So what is the height getting closer to? It's getting close to 4. Does everyone understand that?
Yes.
Yes.
So what about here? Then it's still not very hard. You start up here, figure out what that was equal to. In other words, when x is equal to over here, you put that in, you get some height. Then you put in this value, closer value to 2. Put that in, you get another height. And what is it getting closer to? You can answer that just by putting 2 into for x. So what do you get? You get 2 squared minus 2 plus 2. Did I do that right? I think so. They cancel, you get 4, right? These cancel, and you get 4. So what's the answer? What's the answer?
4.
4, right? Everyone understand this idea?
Yes.
Yes.
So that's what they're talking about. That's what they're asking us to do. So, in general, here's the format for what we're trying to study. So again, what are the pieces of this notation? There have to be what elements in this notation?
The limit.
Okay, well, there has to be the word limit, L-I-M. What else has to be there?
Function.
Function.
We have to have some function in there. What about this? This is probably going to be a number.
Constant.
We're going to have a equal sign. And what else? An x value and the value that it's approaching. Right? Okay, so that's what we want to study now. And how do we read all of the screen? We call it the limit of f as x approaches a. And we say it equals L. Okay, does everyone get that?
Yes.
Yeah.
Okay. Okay. All right. Let's see. And then they say, okay. They say instead of doing this, sometimes we'll get lazy and we'll not lazy, but another way to write it is like this. Okay, so it has the same, basically the same pieces here. So it says F gets, what is, in terms of the graph, here's F. What does F stand for in terms of the graph? I already answered this before, but I want to emphasize it again. What does F stand for in terms of the graph? So if I said, what is f of x when x is here? What do I mean by that? If this is x0, and I say, what is f of x when x is x0? What do I mean by that?
The height.
I mean the height. Let's say I have a sine function. That wasn't a good sine function, but so if I ask you, let's say this is pi. If I say, what is f when x equals pi? When x equals pi, what is f? What do I mean by that?
The value of y.
Yeah, I mean the height. The value of y, which is the height. So what is it in this case for the sine?
0.
So how could we write that? We could say it in English. We could say it as, if I wanted to write it out in words, I would say f is 0 when x is pi. Does everyone agree with this sentence for this picture?
Yes.
F is 0 when x is pi means, when we say f is 0, we mean the height. The height is 0. How about here? Does anybody know when x is pi over 2? I'll give you a hint. So now what can we say? How do we read that? How do I make a sentence like this for this?
F is 1 when x equals 5 or 2.
Right. F is 1. Here's 1, right? This is 1. When x equals pi over 2. Okay? How about here? If this is x squared, make a statement about that. Somebody else, some other voice.
F is 25 when x is 5.
F is 25 when x is 5. Okay, so hopefully you get the idea that when we say F, and we're talking about the picture, we mean the height. Okay, so here we said as x gets close to A, the height gets close to L. And you can say that like this also. As x gets close to A, the height gets close to L. So you can use it, you can write it this way, or you can write it this way. Now, I never use this, rarely, but you could. Okay. Okay, now we have this question. So what does this say? Or did we see this before? Somebody has a weird sound coming out of their microphone. Did we see this before? Did we see this before?
Yes.
What did we see before?
We saw x squared minus 1 over x minus 1.
Right, so we didn't see this actually. But almost, I mean, similar, but not definitely not the same. And actually, this was the same though. X, as x went to 1, that part was the same. Okay. So what's the question here though? Well, let me just draw here, even though I know I don't have much space here. I don't want to switch to a whiteboard right now. So I'm just going to draw right here. So I'm just going to do it like that and like that. And as x gets close to 1, so this function, this is a function. So this function has some kind of picture. I don't know what the picture is, but it has some picture. And what are we asking? As x gets close to 1, what we're asking about what? The height, remember? We're asking about the height of the picture, right? I said the height. F means the height. So here, when x gets close to 1, we're asking about this height. What is it? That's what we want to know. Now, I just made up this picture, so I don't know. It doesn't have anything to do with this function. Does everyone understand?
Yes.
Yes. Okay, but then they mention here something special, and that is, they say, for this function has a problem, a domain problem. What's the domain problem for this function?
X cannot be 1.
Equal to 1.
X cannot be 1, right? If we put in x equals 1 into this, this is x minus 1 over x squared minus 1. What's the numerator when x is 1?
0.
If x equals 1, what do we get?
0
Yeah.
determined.
We get 0
0 over
the top,
0.
Over 0.
0 in the problem. Bad, 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 bad. That's really bad. So we can't put in 0. I'm sorry, we can't put in 1. Okay, does everyone understand that?
Yes.
However, that's not what the question was. The question wasn't when x equals 1. Now you can't read the question anymore because I scribbled all over it. But the question, I'll rewrite it. The question was, let's write it here. The limit as x goes to 1 of x minus 1 over x squared minus 1. That's not asking, that's not putting in 1. This is the subtle value or the subtle importance of the limit. It's not saying what happens when you put in 1. It's saying if you get close to 1. Okay, now let's everybody say that together. So unmute your microphone and let's read this sentence that I'm going to write. Let me write it first. So it's, wait, don't unhook your microphone yet. Hold on, because it's going to be noisy. It is not asking what f is at 1. It is asking what x is near 1. Okay, so does everyone see this question here? This is the question that we were trying to answer. Did everyone see it?
Yes.
Yes, Professor.
Okay, let's read the question first. So I'll read the question. It says, limit as x goes to 1 of this function, x minus 1 over x squared minus 1. Okay, now I'm afraid to do this, but I'm going to do it anyway, just for fun. So I'm going to ask everybody to unmute their microphone. I'm going to turn the volume way down so I can't hear it very loud. And then I want everyone to read this sentence together here, starting here. So turn on your microphone, and then when I say 1, 2, 3, we're going to read it together. It's a really silly thing to do, but let's do it anyway. Okay, 1, 2, 3. This question, it is
It's
Not
not
asking
asking what f is
at
at
one.
1. It
And
is
is asking
what
x
is
near
one
1.
perfect.
One.
Okay, now if we had a recording of that, it would sound really weird. In fact, we do have a recording. Okay, now you can unmute your microphones. But anyway, you have to remember that point. That's why I just did that. It's not saying what happens at 1. So because this function is not defined at 1, so we can't give an answer at 1. It's 0 over 0. It's no good. But that's not what this is asking about. This is asking only near 1. Now, that sounds very mysterious and kind of like, almost like nonsense, right? I mean, what do you mean, near 1? It's not very clear what that means, near 1. So I admit that it's not a great sentence in that sense. But we have to remember that it's not asking what x is at 1. Because this is at 1, there's no answer. All right, now I'm going to take this and I'm going to move to a different screen so that I can show you a little bit better. So let me stop sharing that and go to, just share this. And let me go to here. Okay. So let's go to this thing and let's talk about the same question again. So the limit x, what was it? X minus 1 over x squared minus 1 as x goes to 1. Now, this is when, so we can say, but when x equals 1, we get 0 over 0. So, like, we're confused, very confused. What do you mean what do you mean by this question? It's like, doesn't, it seems like there's not going to be any kind of answer. Okay, so what's the function we're examining here? What's the function we're examining here?
X minus 1 by x squared minus 1.
X minus 1 over x squared minus 1. Okay, we're talking about that function. Now, it seems like this is like a messed up function. We get 0 over 0. Like, this function is probably like completely a mess. You might think that. Because we get 0 over 0. So it's like, how can this function be anything but a mess? But if you look at it carefully, you might recognize that you can sort of rewrite this. So how could we rewrite this? We can use algebra to rewrite this thing. Now, this is a mess, we think it's a mess, but we say, wait, let's just, even though it's a mess, let's have some patience and try and do algebra on it anyway. So what could we do?
The denominator can be written as x minus 1 multiplied by x plus 1.
Ooh. So we notice, wow, look at that. We know that. We remember that from somewhere. And then we do this.
Yeah.
Now it's starting to look like kind of strange. Like, wait a second. Because why? What can we do now?
We can
Divide to x minus 1.
Yeah, we can do this, right? Right?
Yes.
And then what do we get?
1 divided to x plus 1.
Right?
Yes.
Now, this function had a problem at 1, a big problem. It was 0 over 0. But now we just rewrote it like this to here to here. What about this function when x equals 1? Is there such a big problem here?
No.
No, there's no problem at all, really. It's just equal to 1/2, right?
Yes.
That's not exactly, I don't think we call that a problem if it's equal to 1/2. Okay? So suddenly we went from, screaming and yelling to, it's just equal to 1/2. So, okay, do you get this? This was kind of tricky. We started with this, and it had a big problem. And then we went from there to here to here, and now there's no problem anymore when x equals 1. Right?
Yes.
Okay, now, the thing is that we cheated. We cheated. We cheated here. What do I mean by we cheated? Maybe you don't think we cheated. Actually, when I took algebra, they never told me I cheated when I did this. They always said, go ahead and do that. I don't know if they changed the way they taught after that, but they never told me that I cheated when I did this. In fact, they told me that's what I was supposed to do. So I wouldn't call that cheating, but it's a little bit of cheating. Why is it
Because
cheating?
we changed the function, the shape of the function.
Yeah, because when we say some function like x plus x is equal to 2x, when we say that, like here's a function f of x, and here's a function g of x, we say they're equal. When you say two functions are equal, I don't know how, if they often explain this, but when we say two functions are equal, we mean they're equal for every possible value of x, right? So here's a function, and we'll say it's equal to this one, but it better be true for every possible value of x. Let's try when x equals 1. Is it true? So when x equals 1, what do you get? X plus s gives you 2, and this also gives you 2, so they're equal there. How about when x equals -1? What happens? You get -2, and here you also get -2. So if they're equal for every possible value of x, then we can write that f equals g. Okay, everyone understand that idea?
Yes.
Yes.
So now I'm saying that this is, now I'm saying that this is equal to this. But it's not quite true. Because this wasn't even defined at 1. this wasn't even defined at 1, right? We said it was 0 over 0, so that's called not defined at 1. So you can't say that it's equal to this, which was equal to a half at 1. So that wasn't quite true. It wasn't true that these are equal. Because when I put in this, when I put in 1 here, I get 0 over 0. When I put in 1 here, I get a half. So that's not the same. 0 over 0 is not equal to a half. So I lied when I said they're equal. Okay, does everyone understand my argument so far?
Yes.
So, okay, so the idea is though, they're not equal at 0. I'm sorry, they're not equal when x equals 1, but everywhere else they are actually equal. Let's check that. Let's check that. Let's say instead of 1, let's say when x equals 2. So what do you get for this part? What do you get for this part here? When x equals 2, what do you get? You get 2 minus 1 over 2 minus 1 times 2 plus 1. And what do you get for this one? You get 1 over 2 plus 1. Does everyone agree so far?
Yes.
Yes.
Okay, now what do I get here? When I do this part, what do I get? I get 1 over 1 times 3. These are equal, right? And not just that x equals 2. Everywhere, this is equal to this, except one place, except when x equals 1. At x equals 1, they're not equal. So we kind of cheat when we say that this is equal to this, because they're not quite equal. They're, almost equal, but not quite. Does everyone understand the argument that I made here? So let me, I prepared a whole lot of quizzes for the lecture, but it wasn't going to be on this. So, so I don't have any quizzes to give you, and to give you a quiz now is going to take time to make it, so, or to write it down or whatever. So I'm not going to do it now. But normally we would have I'm trying to make it so that we will have just a short, 5 minutes and then a little question, and then another 5 minutes, and another question. So, but today we're not doing that.
Excuse me, Professor.
Yeah.
The quiz is now the function is now showing up.
It is showing up?
Yeah.
The image?
Yeah, the image.
I checked a couple of them and they weren't showing up.
I don't know, Professor, but it's showing up.
Uh-huh.
Yeah.
All right, well, we'll use them next week. We'll go back to that discussion next week.
Okay, Professor.
Okay, so I don't know why they didn't show up on my computer, but apparently now the images are showing up. So maybe, anyway. Okay, so does everybody, so what did I just finish arguing? If you're giving an answer, you have to unmute yourself. What did I just finish arguing?
Except one, these two functions are the same.
Yes. Okay. Except at one, this, let me use another color. Except one, this function and this function are equal. Now, why did I care about any of this? We started this discussion about 20 minutes ago, and I already forgot. Why do I even care? What am I talking about? Who cares?
Because we're not actually going to one.
Okay, anyway.
That we're going near.
Yeah, where did this problem come up? In that book, right? In that other text I was looking at, right?
Yep.
So it came up where? Here. So what did they say? They said, guess the value of this limit. So let's go here. So they wanted us to guess the value of this. At, well, obviously at 1. Guess the value of this thing, right? So, and then we said, wait a second, wait. We said, this is not defined at x equals 1. So what are they talking about? Don't ask me this question, because it's not even defined at 1. It's 0 over 0, right? So we get upset. But then I tried to make everybody say something together. And what did I say? What did we say together? Let's look at it. Where was it? I think I wrote it in the book. Here. We said it's not asking what f is at 1. It's asking near 1. Okay. So we just showed that this function is equal to this function, right? Except at 1. So how about if we knew the graph of this? So anybody know what the graph of that looks like? I think it looks like this. Better use a different color. I think it looks like this. Maybe I'm wrong, but let's suppose it looks like that. So if it looks like that, it's supposed to be a solid line, sorry. So if it looks like that, what are we asking about? Near 1. So near 1, what is this equal to? 1/2. We found that out. So now the original function, this function, is not this. But it is this everywhere except at 1. So this function also looks just like this, except at 1. At 1, we have to draw a big circle there to say there's nothing there. It's not defined there. Whoops, I didn't mean to do that. But the limit question is not asking at 1. So we don't have to say there's a big question mark there, or there's a big open space there. We don't have to say that. We're just saying as we get closer to 1. So as we get closer to 1, what's happening to this function? What do we mean by the word what's happening to this function in terms of the picture? We mean the height. So as we get close to 1, what's happening to the height?
Close to 1/3.
Is it 1/3 or 1/2? Oh, 1/3, sorry. Thank you. So it gets close to 1/3. It doesn't mean that at 1 it's equal to 1/3, because it's not. This is equal to 1/3 at 1, but this is not. That's not what we're asking. I made everybody say that. I said this isn't asking at 1. This is not asking at 1. It's just saying near 1. So you can see what's happening near 1. It's getting closer and closer to 1/3. So finally, with 1 minute overtime, we get the answer is 1/3, even though the function is not defined at 1. But this is not asking what's happening at 1. It's asking near 1. And that answer, we would say, is 1/3. It's getting closer and closer to 1/3. Okay, I think we have to stop now. And there's an attendance code for you to use in the chat box. So please do that. And hopefully next week, we will be able to start doing the quiz agenda. Okay, we're going to do the quiz agenda. Okay, hopefully that will start working next week. And for this week, I will adjust your homework to be related to the discussion we had today. And I will post this video on YouTube also, and give you the link at Manaba. Okay, that's all for today. Have a nice week.
Thank you, Professor.
Thank you, Professor.
Thank you,
Thank you,
Professor.
Professor.
Thank you, Professor.
Thank you, Professor.
Gambate.
Professor, can I ask a question?
Yeah.
I don't need to enter the code until now. I'm wondering like how to enter the code.
Okay, maybe you can share your screen with me after I stop recording here.
Okay.
I'm going to stop recording. No, stop recording.